So I wanted to revisit this problem that I got, the question from a Cal 1 student. If you remember, the problem was something like, given x squared plus y squared equals 169. And I think x was 5 and y was 12. And dx dt was 7, and the question was, what is dy dt? And we said, oh, well, take the derivative with respect to t, algebra, and it's done. Well, that's true, but it really misses the whole point of a problem like this. This is the equation of a circle, radius 13, right? Okay. But when we see this, dx dt, okay, particularly the dt part, right? That indicates that something here is changing with respect to time. Now, circles don't change with respect to time; it's just a circle, okay? So we can't really think of this thing as a circle if we're going to take the derivative with respect to time. So we really should think of this as a circular path, okay? So in other words, something, we can call it a particle, okay, is traveling on a path, right? So if you took a picture of this thing, this path, at any particular moment, that might be what one picture would look like, okay? And the particle would be traveling in this direction, okay? If you took a picture a little bit later, maybe it would look like, I don't know, maybe it would look like this. That's what the picture would look like. This would be gone, right? And the particle would be traveling in this direction, okay? Sometime later, we might see this particle here, and it's traveling in this direction. Okay? So 3 different pictures at 3 different times. We're never going to see the whole circle, okay? So it's a circular path, right? Now, we have here that x is 5, okay? 1, 2, 3, 4, 5. And y is 12. So this is a position. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So at some particular time, our particle is right there, right? Now, we know that that particle is on this circular path, okay? And the direction of travel of something on a circular path is always at 90 degrees to the radius. Okay? So this is our radius here. And the particle at this point in time, right, has to be traveling in that direction, okay? So we know the slope of this line, right? It's rise of 12 and run of 5, and it's positive. Yes? So the slope of this line is rise over run. It's 12 over 5. This line is perpendicular to that line. We know then that the slope of that line is going to be the negative inverse of this, right? Negative 5 over 12. Okay? We know that. Now, it says here that dx dt is 7. So this is the change in x with respect to time, okay? And x is position. So the change in your position with respect to time, that's actually your speed, okay? If you have a direction, can be interpreted as velocity. So this speed, velocity right here, is 7. Okay? Now, the vertical component of this direction, okay, is right here. All right? And this is this is going to be dx dt, and this here is going to be dy dt, right? Now we know that the slope of this line is equal to rise over run, right? And this is the rise. And this is the run. You have two fractions that are equal to each other, okay? You know, you can actually cross multiply, okay? So dy dt is going to be equal to negative, and then it's going to be 35 over 12. Yeah. So these dx dt and dy dt's, okay, they have a meaning when you think of this as representing a circular path and a particle traveling on that path, and now time actually has some sort of an interpretation, okay? If you just take this and you say, oh, we have to take the derivative with respect to time, algebra, and spit this out, okay, it really kind of misses the whole purpose of calculus and what calculus is actually analyzing when we have a dynamic situation like a particle moving on a circular